Hi everyone, this is Miss Tori, and in today's video we are going to talk all about the laws of exponents or the properties of exponents. So stay tuned, we're going to learn all of them in this video. Now guys, make sure that you comment with your first name and then the initial of your last name plus the name of the section of the class you're in. So if you're in the second block, part A, you'd put first name, last name initial, 2A, Math 8. So make sure you put that in the comments so you can get credit for watching this video. Please excuse this little rectangle here with the Google Chrome on it. My laptop is absolutely trying to keep this video from being great, and that's okay, we're going to move on. The very first exponent rule we are going to talk about is the product rule. That is the first one we're going to discuss, which we've been talking about all this past week, last week. We use the product rule when we are multiplying powers. And when we say powers, we're really just talking about multiplying terms that have exponents in there. Multiplying items that have exponents. Now, the rule is very simple. When you multiply powers that have the same base, you add the exponents. So when we multiply some powers that have the same base, we add the exponents. Now let's pause for a minute for vocabulary because we do need to make sure we know what I mean when I say powers and bases and exponents and all of that. So let's say we have a to the 5th power. This whole expression can be called a power because it has a base and an exponent, right? So the big item at the bottom is called the base. Whatever that is, it could be a number, it could be a variable, but it's the big item that's at the bottom. I'm using all these words that start with B. Base is the big item at the bottom. The exponent is the little number on top. When you have all this together, we call it a power. So this first rule, the product rule, what we learn is anytime you have something, a power, like what we see here, and it's being multiplied, so that's product rule, product, multiplication, same thing, we can add the exponents to simplify it. Okay, so we're going to do a couple of examples. Here we see 4 examples that require us to use the product rule in our rules or laws of exponents. So we're going to use this first rule that we just learned. Question 1 shows us multiplication with that dot. We know we're multiplying. We can see that they have the same base, n and n. So all we need to do is keep that base and add the exponents. 2 plus 5 would give us 7. That's our final answer, n to the 7th. It's that straightforward. Number 2, once again, we are multiplying because we see the dot there. And we have 2 powers. We know we can use our product rule. The base is 2. The big item at the bottom is the base, 2 and 2. You don't multiply them, it just stays a 2. Okay, that's a common mistake students make. Don't multiply them, it stays 2. The base stays the same. We add the exponents. 2 plus 3 give us 2 to the 5th. And that is simplified. It said to leave your answer in exponential form, meaning don't change 2 to the 5th to a number. Just leave it as a base with an exponent. Number 3, This is still multiplication. I don't see a dot there, but I know it is because we have these expressions written side by side. Okay, so that does indicate that we're multiplying, so we have to use the product rule. Once again, the base is the same. The big item at the bottom, -2, -2, keep it as a -2. Keep it in parentheses. And just add the exponents. That's all we're doing here. So once again, we have a 7. One more for this rule here. We see multiplication yet again with the dot, meaning we need to do the product rule. Same base, z and z, add the exponents. 10 plus 3 is 13. That's it, okay? Same base, multiplying, add the exponents. Product rule, that's the first one. So moving on to our second rule, the quotient rule. This one we use when we are dividing powers. Remember, quotient, dividing, those terms go together. So the rule tells us when we divide powers with the same base, we subtract the exponents. Once again, very important, the bases have to be the same in order to use the rule. The big number or the big item at the bottom has to be the same in order to use the rule. And then we don't do anything with the base, we just leave it there. The only math we do is subtract the exponents. So let's look at a few examples. Notice in the examples, questions 5 through 8, all of them appear to be a fraction. When we see these types of problems written in fraction form, it is a giveaway that we are dividing. It is a hint to us that we need to use the quotient rule, okay? So in number 5, we can see the fraction bar. We know we're dividing. We need to check, do we have the same base? And we do. The big item at the bottom is R. We have R and R, same base. So we can just actually bring that down. And now we subtract the exponents. 4 minus 3 is 1. Now, you could write a 1 here. But if you're highly skilled, a highly skilled mathematician, we wouldn't write a 1 as an exponent here because we know the invisible 1 is implied that there is a 1 there. So we're just going to leave it as R. Okay. Number 6, same base, MM, same big item at the bottom. So bring down the M and then just subtract the exponents. That's it, M cubed. Number 7, once again, fraction bar. So we know we're using the quotient rule because we're dividing. Check to see if you have the same base. We do, 15 and 15. So keep the 15, subtract the exponents. We have 4 minus an invisible 1. So 4 minus 1 would be 3. We don't do anything else, just leave it. You don't need to change it to a whole number, whatever 15 to the 3rd power is, just leave it. Number 8, do we have the same base? Yes, we're dividing. So we need to subtract the exponents. Now let's pay attention here. 15 is the bigger one, it's on the bottom, right? 7 is on top. So if we did 7 minus 15, we would get a negative number. But we don't want to do that. So what we're going to do is just know that the bigger one is on the bottom. So this answer needs to be on the bottom of the fraction as well. And 7 and 15, that when you subtract, you get an 8. So there's 8 left over on the bottom. Now we can visually explain why this would work. We could do x, 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 x to represent the 7 x's on top. Right? Because x to the 7 just means x times itself 7 times. Okay? Then you would need 15 x's on the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And you could do it this way all the time for every problem, but because it's a lot of time to expand these powers, it's better to just know the rules. These rules are shortcuts, but you can always expand the powers and do this cancellation that you're about to see me do. So anytime you see the same term on the top and the bottom, right? We have x on top, x on the bottom, you can cancel. So we could do top, bottom, cancel, 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 top, bottom, cancel. And then however many we have left would be our answer in whatever position they're in. So these are on the bottom. We have 1, 2, 3, 4, 5, 6, 7, 8. Therefore, it is 1 over x to the 8th because you wouldn't leave this empty. You put a 1 up there to hold the place. Okay, so that is the quotient rule. The next rule we're going to discuss is the zero exponent rule. This talks about a very specific case when you have a power, an expression, a term, and it has 0 as an exponent. So something like x to the 0, for example. Very simple. Anytime, every time you have a 0 as an exponent, it turns this value into 1 every time. It's always a 1. Anything to the 0 power becomes 1. Let's look at a few examples to practice this. So for question 13, we have negative 0.3 in parentheses, letting you know that that whole expression, negative 0.3, is all being raised to the 0 power. It might look special, but really the rule tells us this just turns into 1. There's no math for us to do. Anytime we raise something to the 0 power, it's 1. Okay? 14. Once again, we have an expression inside of parentheses. We have negative 7y. This whole thing is being raised to the 0 power. And that's okay, because it still just becomes 1, right? Now let's look at 15. For number 15, we have negative 7y to the 0. Notice how I said that differently? Notice the differences between 14 and 15. 14 has the negative 7 and the y being raised to the 0 power. For 15, it's just the y, right? So we could rewrite this to make it stand out for us as negative 7 times y to the 0 power. And that might make it a little bit easier to understand. So the negative 7 is here, just kind of out in front on its own, and you can just keep it there. But y to the 0 becomes 1. That's what our rule says. So this is what we have now. Negative 7 times 1, which is just negative 7. That's it. Okay? So the third rule that we discussed, the zero exponent rule, just says anytime you raise something to the 0 power, it's 1. The next rule we're going to discuss is the negative exponent rule. And I kind of explain this a little differently than textbooks do. Try to make a connection to the real world. So, negative thoughts, negative people, right? Negative people have negative thoughts. They're not happy. It's kind of hard to be happy and talk negatively or think negatively. So it can be safe to assume that people who are not happy are the negative people, okay? Same thing with exponents. If you see an exponent that is negative, it means it is not happy with its current position in life, right? There are two possible places an exponent could be. It can be on top of the fraction, it can be on the bottom of the fraction. If it is negative, it is not happy where it is, and it needs to switch positions. So let's look at number 19 to make this example clearer. Right now, I don't see a fraction. I just see w to the negative 6. But even when you don't see a fraction, it's there, just like number ones are always there. So what we really have is w to the negative 6 over 1, right? If we wanted to write it as a fraction. Well, the w to the negative 6 is not happy right now at the top of the fraction. So to make it happy, we can flip it. We can switch its position in life, and we'll put w to the positive 6 on the bottom with the 1 on top. So now it is happy. It's not on the top anymore, it's on the bottom. And once it moves, it's no longer negative. It becomes positive because now it is happy where it is. Okay, so that is the rule with negative exponents. You never want to turn in an answer with negative exponents. It is not completely simplified if it still has negative exponents in it. So you always want to make the negative exponents happy. So let's look at number 20. This 2 to the negative 3, not happy. Doesn't want to be on the bottom. So we'll move it to the top. So it'll become 2 to the positive 3. Okay, now you could put that over 1 if you wanted to show the fraction, but as a highly skilled mathematician, I just cannot put that over 1. But you can, it's not wrong, it's just not highly skilled. Okay, number 21. We have all-inclusive 2m to the negative 3rd power. It's not happy, okay? So we need to make the 2m happy. So we need to move it, right? As it stands now, I don't see a fraction, so that means it's on top. It's not happy there. Let's move it to the bottom. So keep the same expression, 2m in parentheses, but now that it's on the bottom, the 3 is happy, it becomes positive. And just fill your top with the 1. You do have to put a 1 on top. You can't leave the top empty, okay? Number 22, similar, same thing as 21. You have 3a, right? Not happy, it's raised to a negative 3. Let's make it happy. Let's make it a positive exponent. So we'll move it down to the bottom because right now it's on the top. I know it's on the top because I don't see a fraction. So I move it to the bottom and my negative 3 becomes positive 3. And that's as far as we're going to go with those until we see the next rule in just a moment. For the next rule, we are going to look at power of a power. And this is where you take something that has an exponent and raise it to another exponent, right? It has multiple levels. You have something with an exponent, and then you take it to a power as well. It could look like this. 2x squared, and then that raised to the 5th power. So you see you have multiple exponents when you have power of a power, right? Multiple exponents, an exponent that's raised to another one. In this case, whenever you have power of a power, it is similar to the distributive property, which means you need to multiply this top level exponent it has to be multiplied to every exponent on the level beneath it. So it gets multiplied to the invisible 1 right here that you don't see, and it would get multiplied to this 2. So power of a power is similar to the distributive property where you are multiplying the upper level exponent to every exponent on the lower level. We will see some examples to make it clear. So in example 9, we can clearly see we have multiple exponents because we have 2 to the 4th that's also being raised to the 3rd power. So that is my signal that I need to use the power of a power rule. Whenever I see that, the first thing I want to do is make sure every exponent is labeled. Even if highly skilled tells me not to, I like to make sure it's labeled so that I don't leave anything out. But when we look at number 9, there's nothing missing, right? 2 to the 4th power is labeled, no problem. So all I need to do is distribute this 3, the upper level exponent, multiply it to the lower level exponent. Multiply it, right? So this is going to become 2 to the 4 times 3, which would be 12. And that's how you do that, okay? Looking at number 10, I will check and see if there's any powers that don't have their exponents labeled, and in this case they're not. We're good. I do see that I have upper level exponents. This 5 needs to be multiplied or distributed down to the lower level exponent, which is 6. We multiply them. Okay, so the base stays x, and 6 times 5 is 30. Okay, that is the power of a power rule. Now, number 11, we have more than one thing inside the parentheses here. We have 3z squared, and that whole thing is being raised to the 2nd power. I see power of a power. I see upper level exponents and lower level exponents. But remember, the first thing I want to do is to label anything that's not labeled with an exponent. So I can see that 3, the big 3, doesn't have an exponent on it. That's a problem, or it's not a problem, but it would be easier to not make mistakes if I put an exponent on it. So there's an invisible 1. I'm just going to make it visible. Okay, now everything in the parentheses has an exponent. That way I won't make the mistake of forgetting it. I put the 1 there so it stands out to me that I need to distribute this upper level exponent, multiply it by all the lower level ones. Okay, so now I know I keep my 3, and then 1 times 2 is 2. Keep my z, and then 2 times 2 is 4. That's power of a power. Okay. Number 12, same thing. Does everything that is being raised to the power have an exponent in the inside? It doesn't. We don't see it there. So we want to write it in so we don't make a mistake here. Right? Because it might be easy to make a mistake and say, oh, it's just a 2. No, that 2 has to go on every item inside the parentheses. Just like distributive property, it has to be multiplied by every single thing in the parentheses. So the -5 has an invisible 1. The x has an invisible 1. And we're going to take this 2 and distribute it to each one of them. So that's -5 to the 2nd power and x to the 2nd power. Okay. Questions on this, you can drop it down in the comment section if you have questions on this. Now let's look at 16, because it's going to work the exact same way. It doesn't matter that inside the parentheses you got a fraction. It doesn't matter. You still take that upper level exponent and multiply it by every exponent inside. So you want to make sure you have it labeled first. I see this T doesn't have a label, so I want to make sure I put the invisible one, make it visible. And I follow the same exact process, right? 3 goes to the 2, 3 goes to the 1. So I end up with x to the 6th over t to the 3rd. Very important. Power to power, multiply the exponents. Power to power, multiply the exponents. So now we're going to put all of these rules together and simplify some expressions here. So let's look at number 25. To start with, I see a fraction, which might let me know to do the quotient rule, but you have to pay attention. The bases have to be the same, and in 25, they're not. We have an M and an N. So there's actually no simplification as far as that goes. But I also see a negative, unhappy, depressed power because it has a negative exponent. It has n to the negative 2. So we want to fix that. Make it happy, change its position. So I'm going to bring the m to the negative 2 up to the top with the m. And now it becomes a positive 2. And now we're done. There's nothing else we can do because the bases are different. So that's it. That's our answer to 25. Okay? Nothing else can be done because they're not like terms. They have different bases. Okay? 26, once again, a fraction, which would make me think I might have to use the quotient rule, but you want to pay attention. Do you have powers with the same base? And we don't, right? We have an X, we have a Y. But we do have an unhappy X. It has a negative 4. It's not happy. So we need to change its position. We can bring it down. And a lot of people like to keep the variables in alphabetical order. You don't have to, but a lot of people do. So you might want to put X to the 4th in front of the Y. Keep your 3, keep your 15. Now, there's nothing wrong with this. This answer is correct, but we can take it a step further and reduce the actual numbers of this fraction. So 3/15 is the same thing as 1/5. So we'll go ahead and do that. X to the 4th Y. Okay, so the only thing we needed to do for this one was reduce and fix the unhappy exponent, nothing else. Okay, 27. So here I see an expression in parentheses, right beside another expression in parentheses, so I know they're being multiplied. Yes, and since they're being multiplied, we can use the product rule, but only if they have the same base, okay? So I'm going to actually start with the whole numbers, these coefficients here, 2 and 5. These don't have exponents on them, they're just regular numbers. You can actually multiply those together like normal. So we have 10, okay? 2 times 5 is 10. It's just numbers that were out in front. We can do that. Okay, now the x's, look here, we have x, x, same base, being multiplied, so we add the exponents. 2 plus negative 2 gives me a 0. So let's write that down for now. I know we can fix it later, but 10x to the 0. And I'm going to scratch that out just so I know I've already taken care of it. Next, we're going to do the y's. Still multiplication. So we need to add the exponents. The invisible 1 plus 3 gives us y to the 4th. Okay, now you can't turn this in like this, it's done, but when you have a 0 exponent, you have to fix that. Don't turn it in with that 0, don't turn it in with a negative, okay? So x to the 0, we know, turns into a 1, right? That's an easy property. Anything to the 0 turns to a 1. So it just goes away. We're not going to write 1s because we're highly skilled. So 10y to the 4th, okay? 28, number 28. Once again, the Google Chrome tab rectangle is trying to keep this video from being great. Okay, so 28, we have an entire expression that's being raised to an exponent. So here we would need to use the power of a power rule. And remember, I told you, you want to make sure everything has a labeled exponent, so you don't forget anything, you don't leave it out. So let's label the 2 with an invisible 1. Okay, or with a visible 1, I should say. It's already invisible. So now the 2, the r, and the s all have an exponent. So we can go ahead and distribute, multiply this upper level exponent by all of the lower ones. Okay. So bring down the base, we get 2. 1 times negative 3 is negative 3. It's our new exponent. Bring down the base, we get r. Negative 4 times negative 3 is positive 12. That's our new exponent. Next, bring down the base, s. 2 times negative 3 is negative 6 is our new exponent. Now, cannot turn this in this way because you have unhappy people. Don't turn it in with negative exponents. We have to make them happy first, put them in the right position. So let's keep our r to the 12th up top because he's fine where he is. But the 2 to the 3rd power is not happy, so bring him down to the bottom with a positive 3. And bring the s to the bottom with a positive 6. And now everybody's happy and you can turn it in, okay? All right, guys, this has been the video on laws of exponents or properties of exponents. Do rewatch anything that you need to watch. I am going to put the timestamps in the description so you can skip to the specific rule that you need to. But remember, to get credit, you do need to comment your first name, last initial, and the section that you're in. Thanks for watching.